We're going to start this course with a study of functions of more than one variable. And first step here is just going to be seeing what these look like. So we're used to functions of one variable, like in Calc 2, you might have a function f of x equals x squared or something like that. Here, we're going to have functions with more than just x as input. So here's an example of a function of two variables. I would call it f of xy. I've chosen x and y for my variable names. And maybe it's x squared y plus 2y minus 1, say. So there's a function of x and y. And one of the very first things we want to be able to do is just understand what it means to plug in to a function of more than one variable. So if I ask for f of 2, 3, you probably know what this means to do, but just in case, just to be explicit, I want to point out, did that wrong, that we always put the inputs in the same order as we did when we defined the function. So I've got x comma y, that means when I put 2 comma 3, I want 2 for x, 3 for y. So I go through and I just plug in everywhere a 2 for x, a 3 for y, and it looks like I get 4 times 3 gives me 12, plus 6 minus 1, so 17 for f of 2, 3 with this example. All right. We can do this with as many variables as we want, and we'll see in the coming weeks that once you know how to do something for 2 variables, it's usually very easy to do it for 3 or for 4 or for 5. So that jump from 1 variable to 2 takes some thought, but often from 2 to more is straightforward. So now that we've seen f of xy, we can also do an f of xyz. So maybe f of xyz is xy plus z. Or maybe we need even another variable, and so we have a function of x and y and z and w. Maybe it's e to the x plus w times y, z, say. So there's a function of 4 variables, x and y and z and w. All right, so these functions of more than one variable are really useful because life depends on a lot of stuff. So everything that happens in our life depends on all sorts of different variables. So for example, money in your bank account. So money in your bank account is going to depend on different things. So it's going to depend on that principal. How much did you initially deposit into that account? It's going to depend on what the interest rate is on your account. It's going to depend on how long you leave that money in your account. And if this is a savings account that you only put money into once and you let it sit there, this is it. But maybe you're also withdrawing some money from it. So that'll certainly play into this. And maybe you're adding more money to it. So extra deposits will be in there also. And maybe there's a fee for the savings account, so that would come out. So most problems in life have all these different variables that we have to consider. So one other, there are some places that have sort of a set up salary scale. And one of the common ways to do this is your salary depends on your years of service. So they have some kind of a function, and you plug in how many years you've been working there, and you plug in what your highest degree earned is. So for example, if you're a teacher, often you have a bachelor's degree or a master's degree, you get that pay bump for the master's degree. So this is a place where your salary would be affected by these, and it would be a function of these variables. All right, we're going to study one more and do a few things with it. So this one that we're looking at here is called the Cobb-Douglas production function. Okay, and what it says is that the production output, we're gonna call a function P of xy, P for production. And it depends on your labor input, which we'll call X, and your capital input, which we'll call Y. All right, so the labor input is maybe measured in something like person hours. So how many hours worth of labor did people put into this process to manufacture whatever you're producing? And then the capital input is the kind of other stuff. So the materials that you have to use in your factory, the space itself, any kind of overhead like that, the machinery that you need for your factory, all of that would be a capital input. All right, so one example of this, and the Cobb-Douglas production function really is more like a kind of format for a function, and we're gonna put some specific numbers to it. So we're gonna call it 20, x to the 1/3, y to the 2/3. And if you had a different factory, you would change some of these numbers. But this general format where we have a constant, we have x and y to two exponents that add to 1. That's the important part here. This is called the Cobb-Douglas kind of production function format. And we're going to see what those coefficients adding to the exponents adding to 1 means in a minute. All right, so this is the example we're looking at. Suppose we have 8 units of labor and 1 unit of capital. Let's figure out how much we produce in our factory. All right, and then the units on labor and capital might be something different. So 8 units of labor might mean 800 person hours, or it might mean 80,000 person hours. We would scale that appropriately for our setting. And then again, 1 unit of capital could mean lots of different things also. Maybe it means $100,000 worth or $1 million worth, depending on the size of our factory. All right, so when we ask how much are we producing, we're asking what's P of 8, 1. 8 was our labor input, that's what we called X. Y was our capital input, that's what we called that. So we have 1 unit of capital, so we're plugging in 1 for Y. So we get 20, and then X, which is 8 to the 1/3, and Y, which is 1 to the 2/3, and we're just plugging in and figuring out what happens. So 20, 8 to the 1/3, that's cubed root of 8, which is 2, and 1 to the 2/3 is just 1, so we end up with 40 units of units produced. All right, so now we're going to do one more thing with this, which is what if we scale our labor and our capital? Okay, so we're going to talk about scaling up. So I used to have 8, now I'm going to scale up to say 8K units of labor. And K units of capital. So maybe K is 2, and so I'm doubling my labor input and my capital input. Okay. So if we look at what happens with our production, now instead of 8 and 1, we're putting in, say, 16 and 2, or 24 and 3, or 80 and 10, something like that. If we plug that in, we've now got 20, and then 8K to the 1/3, and K to the 2/3. And we clean this up a little bit by distributing that 1/3, bringing it into both pieces parentheses. So now we've got 20. 8 to the 1/3, we already did that before. That's 2 cubed root of 8. And now look at our k's. So we've got k to the 1/3, k to the 2/3. Well, we add those exponents, and 1/3 plus 2/3 gives us k to the 3/3, or k to the 1st, right? So we end up with 40k. Now, what's interesting here is that when we started with 8 and 1 as our inputs, we got 40. And now when we scaled up by k for our inputs, we also scaled up by k for our outputs. So this is k times our original production. All right, so what we saw there, when we scale the inputs, we get the same scaling factor in what we produce. It's called constant returns to scale. And all it depends on is that sum of those coefficients on x and y, not coefficients, the sum of the exponents on x and y, adding to 1 is what gave us this constant returns to scale. All right, we're going to do one more example. We're going to build this function. So we're going to say, suppose we're going to build an aquarium, and we want it to be 1.5 feet in width, 3 feet in length, and 2 feet deep. All right. So we can build this aquarium, and we want it to be those sizes. Here's where our function comes in. To build this, we need to buy our materials. So we're going to think about the sides of our aquarium are going to be made of glass. So all of those 4 sides cost some amount. So we're going to call it X dollars per square foot. And then the plastic on the bottom is going to be different. It's a cheaper material usually. So the bottom doesn't need to be glass. It doesn't need to be translucent. So we just get some kind of plastic for the bottom. And it costs Y dollars per square foot. So the function that we're going to come up with here is a cost function. So find a function for the cost of the aquarium that we want. All right. So in order to start this is a classic problem where it really is going to help to draw this box. It may feel silly to just draw a box over and over again, but it's sometimes really useful for these problems. So we're going to draw our box, and I kind of did that backside not so well, but that's okay. So there's our box, and I didn't draw it especially well to scale because we know what the dimensions are. So let's call the length 3, and let's say that's our 3. Our depth, our depth, we want to think about, since this is an aquarium, we want the depth to be actually the depth of the water. So that's our 2. And then our 1.5 is that kind of width, so the back direction. All right, so there's our box. Let's figure out what our cost is going to be. I'm going to call it C of XY. And let's go face by face. So we've got this front face right here, right in front. The dimensions of that front face are 3 by 2. So 3 times 2, that's the front face. And then it costs X dollars per square foot. So we're going to multiply that 6 by X. And then the back side of our aquarium is exactly the same dimensions, right? It's 3 by 2. So we're going to take 2 of those. So this is really the front and the back are going to be 2 times 3 times 2 times X. All right? So that's the front and the back taken care of. The 2 sides, the dimensions of each side, they're 2 in depth and 1.5 in width. Okay. And then it costs another X dollars per square foot for that side. And again, there's a left side and a right side, so there are actually 2 of them. So this is the left and right. And I'm going to continue my function down here because I ran out of room on this side. So we've got the front and the back, the left and the right, and then there's no top for our aquarium. We didn't take that into consideration, but we do have a bottom. So the bottom there is 3 times 1.5. Those are the dimensions of it. And the bottom costs Y dollars per square foot. We don't have a top, so we don't have double this. We just have the 1 bottom. All right, so if we clean this up, this is our cost function. So we've got 2 times 6, so 12x for the front and the back. The left and the right were 2 times 1.5, so that's 3 times another 2 is 6 more, times the X dollars per square foot. And then the bottom, 3 times 1.5 gives us a 4.5 Y. And we can clean this up even further because we've got those X's in common, so we can combine like terms. So we end up with 18x plus 4.5y. All right, so this kind of problem we're going to see later also. So we did this aquarium and we knew what its dimensions were, but the problems that we're headed toward eventually are maximizing and minimizing things. So if we didn't know the dimensions that we wanted, but we knew, say, the volume that we wanted for our aquarium, we knew how much water we wanted it to hold, we could set up a function for its cost and try to minimize that cost with our given volume. So we'll see that kind of problem soon.